Welcome to another deep dive, and today we're going to be looking at a fascinating story, really, about how our understanding of matter has developed over time.
Hmm.
Specifically, we're going to be focusing on the work of John Dalton, a Quaker from England,
Hmm.
and how he really revolutionized the way we think about the stuff that makes up, well, everything.
Right.
We're going to be using, as our guide, this Spanish language biography, 23 Dalton La Teoria Atomica,
Okay.
which dives into his life and his work and the impact he had.
Cool.
So we're going to try to unravel the story of this guy who was seemingly unassuming,
Yeah.
but really made a huge impact.
It's interesting because the idea of atoms, right, like the things that make up matter, it goes way back. If you think about ancient Greece, you have Democritus and Leucippus.
Okay.
They were philosophers
Right.
who had this idea that there were these tiny particles called atomos that everything was made of. And they were indivisible.
That's amazing that that idea is that old, right?
Yeah.
Like without modern scientific instrumentation, they were able to sort of think about that.
I know.
But I mean, that was all philosophical musing, right?
Yeah, yeah.
It wasn't until centuries later that scientists really started applying a more rigorous and experimental approach
Right.
to chemistry and trying to understand matter.
Yeah, Robert Boyle was kind of a trailblazer in that regard, like paving the way for modern chemistry.
So, then we get to figures like Lavoisier and Proust.
Yeah.
And Lavoisier is really known for his law of conservation of mass, right? Which states that matter can't be created or destroyed.
Right.
Seems obvious now.
Right.
But back then, it was a pretty radical idea, right?
Yeah, it was.
And then Proust's law of definite proportions showed that a specific compound always contains the same proportion of elements by mass. So it's like these laws were puzzle pieces.
Yeah.
They hinted at some underlying structure, but they hadn't quite put it all together yet.
Yeah, it was Dalton who kind of took those clues and unlocked the secrets of the atom.
So this guy Dalton,
Yeah.
tell me about him. What was he like?
Well, he was a really interesting guy, actually. He was a Quaker, deeply religious man, very humble. And he had a lot of passions that extended beyond chemistry. Like he was really into meteorology, botany.
Yeah, he's known for his meticulous 57 years worth
I know.
of weather observations. Like, who does that?
Right. So dedicated. But, it wasn't just a hobby for him, Yeah. I think he was really driven by curiosity about the world. And that curiosity led him to study gases in the atmosphere. And that ultimately brought him to the atom.
And we also can't forget that he was colorblind.
Yeah.
Right. And even turned this sort of personal challenge into a scientific quest by researching it and actually contributing to our understanding of how we see.
Yeah.
It's now called Daltonism.
It is, yeah.
So it's really cool to see how our own personal experiences can actually fuel scientific breakthroughs sometime.
Yeah, absolutely. It just shows his meticulous nature and his dedication to really figuring things out,
So this fascination with gases wasn't just about the weather.
No.
Right.
He was really intrigued by how they behaved, how they mixed, how they exerted pressure.
Yeah. And this is where things get really interesting because in 1803, he formulates the law of partial pressures. So tell me a little bit about that.
So basically, this law states that the total pressure of a mixed gas is the sum of the pressures each gas would exert if it were alone. So it's like each of the gas is doing its own thing,
Right.
independent of the others.
So I'm starting to see a connection here.
Yeah.
If each gas is acting independently, wouldn't that suggest that they're made of distinct particles?
Exactly. Like that was his aha moment. And that led him to this revolutionary idea, the concept of relative atomic weights.
Okay, so now he's starting to apply numbers
Yeah,
to these invisible things.
exactly. He realized that if atoms were real, they must have different weights, right? Because that would explain why some substances are heavier than others, even if they have the same volume.
Yeah.
Right.
So how did he figure that out? How did he figure out these weights?
Well, he started with hydrogen,
Okay.
which is the lightest element, and he assigned it a weight of 1.
Okay.
And then, by carefully analyzing the proportions in which elements combine to form compounds, He could calculate the relative weights of other elements. So, for example, if you have 2 grams of hydrogen combining with 16 grams of oxygen to form water, oxygen would have a relative atomic weight of 16.
So it's like a giant atomic puzzle.
Exactly.
You know, you're trying to figure out all the pieces and how they fit together.
Yeah.
But what's amazing to me is that he presented his first table of these atomic weights, not in some fancy lab or university, but at the Manchester Literary and Philosophical Society, the Lyd and Phil, which is just this group of people who love knowledge.
Yeah, it's really cool.
Right. It shows that groundbreaking science can happen anywhere.
Totally.
You know, if there's that spark of curiosity and a passion for discovery.
Yeah.
But Dalton wasn't done yet.
No.
He had a much bigger picture in mind, right?
Yeah, he took all these insights like the partial pressure, you know, relative atomic weights, and he wanted to kind of weave them together into a comprehensive theory.
A theory that would change the course of chemistry forever.
Yeah.
And it all culminated in this book, A New System of Chemical Philosophy, published in 1808. And really, that book laid out his atomic theory, which sought to answer the fundamental question, what is matter made of?
Yeah. It really was a watershed moment, this book.
Yeah.
A New System of Chemical Philosophy. It laid out his atomic theory in a way that nobody had ever done before.
So let's break it down. What were those groundbreaking postulates?
Well, the first and most important one is that all matter is made up of these tiny indivisible particles called atoms.
Okay, so he was taking this ancient Greek idea and giving it a solid...
a scientific basis.
Scientific basis.
Right. Not just a philosophical musing anymore.
So he brought back the atom, but with evidence.
With evidence.
How else?
So he argued that atoms of the same element are identical in mass and properties. So this explains why.
So every oxygen atom behaves like every other oxygen atom.
Exactly.
That's what gives them their unique fingerprint.
Right, exactly.
Okay. So what about different elements, though?
Well, he said that atoms of different elements have different masses.
Okay.
And this is why a lump of lead feels much heavier than a lump of carbon, even if they're the same size.
Yeah.
It comes down to the weight of those individual atoms.
So now we're starting to see how the properties of elements are connected to their atomic structure.
Right.
Did he stop there?
No, not at all.
Okay.
He went on to explain how these atoms combine to form compounds. And he proposed that atoms combine in these simple whole number ratios.
Okay.
This is why water is always H2O.
2 hydrogens, 1 oxygen?
2 hydrogen atoms for every 1 oxygen atom.
It's like a recipe.
Right. You can't have half an atom.
Right. So you can't have half an atom in the recipe.
No, exactly.
So it's so elegant, though, this idea.
It is.
That explains why compounds have these fixed compositions.
Yeah.
But what about the interaction between these atoms? How do they actually stick together?
He believed that they were held together in compounds by forces of attraction.
Okay.
So there were these invisible forces at play that governed the behavior of these tiny particles.
And finally, he ties this back to Lavoisier's work, right?
Yes.
The law of conservation of mass.
Right. He proposed that chemical reactions just involve the rearrangement of atoms.
Okay.
They're not created, they're not destroyed.
They might swap partners. They might change configurations.
Right.
But they're always there.
Yeah.
That's so cool. So it's all coming together now.
Yeah.
His atomic theory was like this master key, unlocking all these secrets of chemistry.
Right. It's like this framework for understanding it all.
It explains why elements have these fixed properties, what compounds have constant compositions, and why matter can't be created or destroyed.
Right.
But as with all science, every answer leads to new questions.
Of course.
In Dalton's theory, as groundbreaking as it was, it did face some challenges.
It did.
Right. Especially when you start talking about the work of Joseph Louis Gay-Lussac.
Yeah, his law of combining volumes kind of threw a wrench into Dalton's very neat and tidy atomic world.
So remind me, what were Gay-Lussac's findings?
Okay, so Gay-Lussac, he observed that gases combined in these simple volume ratios when they reacted. For example, 2 volumes of hydrogen gas would react with 1 volume of oxygen gas to produce 2 volumes of water vapor.
So that doesn't seem to fit with this idea that they're combining in 1-to-1 ratios.
Right.
Was Dalton wrong?
Well, not necessarily. It needed a bit of tweaking. It needed a new perspective. And that's where Amedeo Avogadro comes in.
Avogadro.
Yeah. He was an Italian scientist, and in 1811, he proposed a brilliant hypothesis.
What was it?
He said that equal volumes of gases at the same temperature and pressure contain the same number of molecules.
Molecules.
Molecules. We're adding another layer here.
We're adding another layer.
But it was a necessary layer.
Okay.
Because his hypothesis reconciled Gay-Lussac's findings with Dalton's theory.
Oh.
So it turns out that some elements, like oxygen,
Right.
they exist as diatomic molecules, meaning two atoms bonded together.
Okay.
So when those two volumes of hydrogen react with one volume of oxygen,
Right.
it's actually two hydrogen molecules reacting with one oxygen molecule, producing two water molecules.
So it wasn't one-to-one atoms.
Right.
It was one-to-one molecules.
Exactly.
So clever. But wasn't there some issue with this hypothesis being ignored for a while?
There was, yeah. It actually took almost 50 years.
Wow.
For Avogadro's ideas to be widely accepted.
Wow.
It wasn't until 1860, at the first International Chemical Congress in Karlsruhe, that his hypothesis was finally recognized.
It's wild that even the best ideas can sometimes take so long to catch on.
I know.
But ultimately, Avogadro's hypothesis really strengthened Dalton's atomic theory.
It did.
But the story doesn't end there, right? We're about to enter a whole new chapter in atomic theory, one where we begin to actually prove the existence of these elusive particles.
Yeah, this is where things get really exciting. It's like physics crashes into chemistry. We're talking about the late 19th and early 20th centuries when there were monumental discoveries that forever changed how we think about the atom.
Okay, so we've gone from these ancient Greek musings to Dalton's elegant theory to Avogadro's clarifying hypothesis. What happens next in this atomic adventure?
Well, up until this point, the atom was still very much a theoretical concept.
Right.
A very useful model, don't get me wrong, but there was no direct evidence. It was like, we think it's there, it works, but can we prove it?
Yeah.
And then in 1896, a serendipitous discovery rocked the scientific world.
Henri Becquerel.
Yeah.
The discovery of radioactivity.
Radioactivity, yes. The uranium salts that mysteriously fogged up his photographic plates.
What a happy accident.
I know. It was completely by chance. He wasn't even looking for it.
But sometimes the greatest discoveries happen when you least expect them.
I know, it's so true. And this accidental discovery opened up a whole new realm of exploration.
Leading to Marie and Pierre Curie.
Yes, pioneers in the study of radioactivity.
What an incredible duo.
I know. They were working with these incredibly dangerous substances, right? Isolating new elements.
Yeah.
Polonium and radium from uranium ore.
Yeah, I can't imagine handling those materials back then.
Yeah.
Knowing what we know now about the dangers.
Yeah.
But their work showed that certain atoms, these heavy atoms like uranium, they were spontaneously decaying, emitting this energy and turning into other elements.
Yeah.
It just shattered this idea that the atom was unchanging.
Right. Dalton's indivisible atom was starting to crack a little.
What happened next?
Okay, so at the same time, scientists are tinkering with these things called cathode ray tubes.
Okay.
Basically, they were these glass tubes that had most of the air pumped out.
Yeah.
And when they applied a high voltage to them, something really weird happened. A beam of something would shoot from the negative electrode, the cathode, to the positive one.
It sounds like science fiction.
I know, it's crazy. And so the big question was, what was this beam made of?
What is this mysterious beam?
Exactly. So J.J. Thomson, a British physicist, he conducted all these really cool experiments to figure out what these cathode rays were made of.
What did he find?
He discovered that they were composed of these tiny negatively charged particles.
Okay.
Much, much smaller than any atom known at the time. And he called them corpuscles.
Okay.
But we now know them as electrons.
Electrons. The first subatomic particle to be discovered.
Yeah, it was a big deal.
That's amazing.
It proved that atoms were not the most fundamental building blocks. There was something even smaller.
Right. So if atoms have these negatively charged electrons, how can they be neutral overall?
That's a good question, right?
Yeah.
You can't just have these negative charges floating around in there. Something has to be balancing them out.
Yeah.
So Thomson proposed a model that became known as the plum pudding model.
The plum pudding model.
Yeah, where he imagined the atom as this positively charged sphere with the negatively charged electrons embedded in it.
Okay, so the positive charges are like the pudding.
Yeah.
And the electrons are like the plums.
Yeah, exactly.
That's a very delicious way to imagine an atom.
It was a clever analogy at the time, yeah.
So Thomson's model acknowledged subatomic particles and tried to explain why the atom is neutral.
Right.
But as we'll see, the true structure of the atom was even more remarkable.
It is, yeah. That's where another giant of physics enters the scene. Ernest Rutherford.
Rutherford, the one who conducted the gold foil experiment.
The famous gold foil experiment, yeah.
Okay, so remind me about this.
So in 1911, he designed this experiment
Okay.
where he bombarded a very thin gold foil with alpha particles, which are basically helium atoms stripped of their electrons so they have a positive charge.
Okay, so he was shooting these tiny little bullets
Yeah.
at a sheet of gold.
Pretty much.
What was he hoping to learn from this?
Well, based on Thomson's plum pudding model, Rutherford expected the alpha particles to pass through the gold foil with only slight deflections.
So it's just kind of zip right through?
Yeah, because if the positive charge was spread out evenly, there wouldn't be any areas that were really concentrated to repel the alpha particles strongly.
So he thought they would just go straight through?
Pretty much. But what he observed was shocking. While most of the alpha particles did pass straight through, a small fraction were deflected at very large angles. And some even bounced straight back.
Wait, hold on. These particles were ricocheting off something inside these atoms?
I know.
Like as if they were hitting a wall?
Exactly. Like as if they were hitting something incredibly small and dense within the gold atoms.
So the plum pudding bottle was out?
Out the window.
Okay.
Rutherford concluded that the positive charge of the atom and most of its mass was concentrated in a tiny central nucleus.
So instead of this evenly spread out pudding, it was like this dense core with the electrons orbiting around it.
Yeah, a nuclear atom.
The nuclear atom.
A mostly empty space with this tiny, dense, positively charged nucleus at the center. And those negatively charged electrons orbiting around it.
So like our solar system, instead of having the sun spread out, it was all concentrated.
Right, all concentrated into a tiny core.
This is a huge change in our understanding.
It was monumental, yeah.
But even with this new model, there were still some puzzles to solve, right?
There were.
Like, how do the electrons stay in orbit around the nucleus without crashing into it?
Yeah, according to classical physics, those electrons should be spiraling inward and collapsing into the nucleus, but they don't.
So Rutherford's model was a huge step forward.
It was.
But it needed refining.
It did.
And that brings us to Niels Bohr.
Ah, yes, Niels Bohr.
He's the one who brought quantum theory into the picture.
He did. He was a Danish physicist. And in 1913, he proposed this model that just completely revolutionized everything.
What was it?
He built upon Rutherford's work, but he said that electrons can only exist in these very specific energy levels or orbits around the nucleus.
Okay, so instead of just spiraling inward, they're restricted to these certain orbits, like lanes on a highway.
That's a good analogy, yeah. He called these allowed orbits stationary states. And he said that electrons could only jump between these energy levels by either absorbing or emitting energy.
So they can go up or down. But they can't just be anywhere in between.
Exactly.
Like they're riding an atomic elevator.
Yeah.
They can go to different floors. But they can't just stop in the middle.
Exactly.
And when they jump from a higher level down to a lower level, they emit a photon of light.
Yes.
With this specific color.
Or wavelength, right?
So this explains why different elements emit different colors when they're heated.
Yes, it's all about those energy levels.
So this model, this is a huge breakthrough.
It was, yeah. It explained the spectrum of light emitted by hydrogen, which had puzzled scientists for years.
But like all the models before it, even Bohr's model had its limitations, right?
It did, yeah.
It worked well for hydrogen.
Yeah.
Which is a simple atom.
Right.
But when you start getting into the more complex atoms, it didn't quite work.
Right.
So science is a story of refining these models.
Always refining, always improving.
Yeah.
As we gain new knowledge.
And that brings us to another groundbreaking contribution that completely changed how we think about electrons.
Right.
The Schrödinger equation.
Yeah.
Schrödinger. Wasn't he the one with the cat in a box?
The cat in a box, yeah.
Okay.
That was Erwin Schrödinger, an Austrian physicist, and in 1926 he developed this equation that didn't describe electrons as particles orbiting the nucleus, but as waves.
So electrons are particles and waves.
I know, it's a little mind-bending.
It's mind-bending.
It's one of the amazing things about quantum mechanics.
How's that possible?
Well, we call it wave-particle duality.
Okay.
Sometimes they act like particles, sometimes they act like waves. And Schrödinger's equation allowed us to calculate the probability of finding an electron in a particular region around the nucleus.
So instead of this tiny ball whizzing around,
Yeah.
we have this fuzzy cloud of probability.
Exactly.
Where it could be anywhere within that cloud.
Exactly. We call these electron orbitals.
Electron orbitals.
And they determine how atoms bond together to form molecules, which is like the basis of modern chemistry.
It's amazing to think that the entire world around us, all the substances, all the different materials, it all boils down to these fuzzy clouds.
It does.
Of probability
interacting
with each other.
Yeah.
But there's more.
There is.
Those protons and neutrons, they make up the nucleus.
Yeah.
It turns out they're not fundamental either.
They're not.
There's something smaller than a proton and a neutron.
Much smaller.
This is getting tiny.
I know.
What is it?
So in the 1960s, physicists discovered that protons and neutrons are made up of even tinier particles called quarks.
Quarks. I've been trying to wrap my head around this.
I know, it's getting down there.
If the atom is like a house,
okay,
and the nucleus is like a room in that house,
okay,
and the protons and neutrons are like pieces of furniture in that room.
Yeah.
Quarks are like the atoms that make up the furniture.
Yeah. That's a really good analogy.
Okay.
Yeah, quarks are the fundamental building blocks, as far as we know.
So we've gone from atoms to electrons to protons and neutrons to quarks.
Right.
It's this journey into the heart of matter.
It is.
Is this the end?
That's the big question.
Are quarks the smallest?
We don't know.
We don't know.
That's what particle physicists are trying to figure out.
They're still looking.
Right? They use these giant particle accelerators to smash these particles together at incredibly high speeds.
So it's like peeling back the layers of a cosmic onion.
Yeah.
Who knows what mysteries are waiting to be uncovered in the quantum realm?
It's pretty mind-boggling to think about.
And it all started with this guy, John Dalton.
It did.
This Quaker from England.
Yeah.
Who just had this simple idea that matter is made of atoms.
Such a simple but powerful idea.
And it led us on this journey.
It did.
From his spheres to Schrodinger's equations to quarks.
It's really incredible.
It's this odyssey of discovery.
It is.
And who knows what the future holds.
Right. Maybe we'll discover even more fundamental particles.
Maybe we'll find something even smaller.
You never know.
But this is a real testament to our curiosity and our desire to understand the world.
It is. The story of the atom is still being written.
And it's a story that reminds us that even our most established theories are always subject to change.
Of course, science is a process.
Right. As we learn more,
right,
we have to refine, we have to adapt.
Yeah.
So Dalton's legacy lives on, not just in chemistry textbooks, but in the spirit of scientific inquiry itself.
Absolutely.
The next time you look at, well, anything, just remember that this is a product of this amazing journey we've taken.
Yeah.
Understand the building blocks of the universe.
It's incredible.
Never stop asking questions.
I never stop.
Thanks for joining us on this deep dive into the atom.
Thanks for having me.
Until next time. So last time we left off with Rutherford's model.
Yeah.
This revolutionary idea of an atom with a nucleus at the center.
Right.
And these electrons orbiting around it.
Yeah, but there was a problem.
There was a problem.
Those electrons should be spiraling inward
right,
and crashing into the nucleus.
Right. That's what classical physics would tell us.
Yeah, it just couldn't explain why atoms were stable or why they emitted those specific colors of light when heated.
Right. Like we were missing something.
We were.
And that's where Niels Bohr comes in.
Niels Bohr, yeah.
He's the one who brings quantum theory into the picture.
He does. He was a Danish physicist.
Okay.
And in 1913, he proposed a new model of the atom.
Okay, what was it?
So he built on Rutherford's model, but he added a twist.
Okay.
Electrons can only exist in specific energy levels around the nucleus.
So instead of just spiraling in, they can only be in these certain orbits?
Exactly, like lanes on a highway.
Okay, I like that analogy.
He called these allowed orbits stationary states.
Stationary states.
And electrons can jump between these levels by absorbing or emitting energy in the form of light.
So they can go up or down, but they can't be anywhere in between.
Exactly.
Like an atomic elevator.
I love it.
They can go to different floors, but they can't just stop in the middle.
Right, exactly.
So when an electron jumps from a higher energy level to a lower one, it emits a photon of light of a specific color.
Yes.
So this is why different elements emit different colors.
It all comes down to those energy levels.
That's incredible. So this is a big deal, right?
Huge. It successfully explained the spectrum of light emitted by hydrogen.
Which had stumped scientists for a while.
For years,
That even Bohr's model had limitations.
It did.
It worked well for simple atoms like hydrogen.
Yeah.
But when you get into the more complex atoms, it didn't quite explain everything.
Right, and that's where we come to another groundbreaking contribution.
Okay.
The Schrödinger equation.
Schrödinger, that's the one with the cat.
A cat in a box, yes.
Okay.
That was Erwin Schrödinger, an Austrian physicist. Okay. And in 1926, he developed an equation that describes electrons not as particles orbiting the nucleus, but as waves.
Wait, so they're both. How is that possible?
It's one of the mind-bending things about quantum mechanics.
Yeah.
It's called wave-particle duality. Sometimes they act like particles.
Right.
Sometimes they act like waves.
So this equation,
Yeah.
it lets us calculate the probability of finding an electron
Exactly.
in a specific spot.
Right. So instead of this tiny ball whizzing around, it's more like a fuzzy cloud.
Like a cloud of probability.
Yes, where it could be anywhere within that cloud.
And we call those electron orbitals.
We do. And these orbitals determine how atoms bond to form molecules.
So it's like the foundation of modern chemistry.
See much, yeah.
So all this complexity in the world.
Yeah.
All the substances and material.
I know, it's crazy.
It comes down to these fuzzy clouds interacting.
It's amazing.
But we're not done yet.
No, not quite.
We have these protons and neutrons. They make up the nucleus.
They do.
But it turns out they're not fundamental either.
No, they're not.
There's something smaller.
They're much smaller.
We're going really small now.
We are. So in the 1960s, physicists discovered that protons and neutrons are made of even tinier particles.
Okay, what are they called?
Quarks.
Quarks. I'm trying to picture this.
I know, it's hard to wrap your head around.
So if the atom is like a house, the nucleus is like a room.
Okay.
And the protons and neutrons are furniture in that room.
Yeah.
Quarks are like the atoms that make up the furniture.
That's a great analogy.
So we've gone from atoms to electrons to protons and neutrons to quarks.
We have.
Like this journey into the very essence of matter.
The heart of matter.
Is this the end of the line?
We don't know.
Are quarks the smallest things?
That's the big question, right? That's what particle physicists are trying to figure out.
They're still looking.
Yeah, with these giant particle accelerators.
Right, they're smashing things together.
Yeah, trying to break them apart.
To see what's inside.
Like
peeling back the layers of a cosmic onion.
I love that.
Who knows what mysteries are out there?
So many, it's mind-boggling.
And it all started with John Dalton.
It did. This unassuming guy.
This Quaker from England.
Yeah.
Who had this simple idea.
That matter is made of atoms.
From Dalton's indivisible spheres to Schrödinger's waves to quarks.
It's been quite a journey.
What an incredible story of scientific discovery.
It really is.
And who knows what the future holds?
Who knows? Maybe we'll find something even smaller than quarks.
It's amazing to think about.
It is.
It's really a testament to our curiosity.
It is.
And our desire to understand the world.
And that desire has driven so much progress.
This story of the atom, it's still being written.
It is. We're still learning.
And it reminds us that even the best theories can change.
Science is a process, right? It's always evolving.
As we learn more, we have to refine.
Right. We have to adapt.
So Dalton's legacy, it's not just in the chemistry books.
No.
It's in this spirit of scientific inquiry.
Absolutely.
So next time you look at, anything.
Anything at all.
Just think about the journey we've taken.
Yeah.
To understand the building blocks of everything.
It's pretty remarkable.
And never stop asking questions.
Never stop.
Thanks for joining us for this deep dive into the atom.
It's been a pleasure.
Until next time.